Look at that. Dropped it. Okay, so we're doing homework number 11. Wow, semester is just flying by. And this is our last homework for particle kinetics. After this, we're going to have exam 2. Right, so this is the last topic on exam 2 and particle kinetics. So these are impact problems, collision problems, and we have these two pucks that are going to hit each other. And this one, A, the blue one, is 25 kilograms and it's moving at 5 meters per second to the left. And this little kind of, I don't know, call it, it's kind of green. It's 1.5 kilograms, it's moving 3 meters per second. And so they're kind of offset so that the angle that's formed right here from the vertical is 25 degrees. And the coefficient of restitution is 0.7. We're going to neglect friction. And we want to find the velocity of each of the puck. And we want to find them as a magnitude and direction with respect to horizontal with a quadrant with the thing. Okay, so I've set up the problem on my paper. And here's all the information that we need. So one of the first things I should do probably is draw my impulse and momentum diagram, right? So I'll start out with my initial and my impulse and then my final. Don't neglect the diagrams. Important stuff. So sometimes I'll let's see, what size did I use right here? I used something like this right here. I'll put them over here too. I'll draw them the same guy over here. It's nice to make like nice looking drawings. It's nice to make nice drawings, sure. Something like that. Probably like that guy. And I like to separate them out just a little tiny bit over here in this diagram. And then there's actually a collision for this one. And then for this one, maybe separate them out just a little bit again. Okay. Let's hit plus and equals right there. So for this guy, he's moving right here, and he's moving right here. At impact, we have these equal and opposite things taking place right there. And I like to put a little explosion because it's the little things in life that make it worth living, right? And then over here, maybe I'm gonna wait a second for this. Let's see. Okay, so what's a good idea is to establish a coordinate system based like this right here. And I'm going to double check my coordinate system. What did I decide? I decided to make right here. So this is the normal and this is the tangential. But what did I decide to make normal? I decided, I'm going to put the coordinate system over here, that this is normal, EN, and this is tangential right there, ET. Okay? And we can look at the angles. I'm actually going to do a coordinate transformation as part of this thing. Yeah, I know. All this stuff is connected to each other. But I can first kind of like draw out these components right here. So I'm going to kind of dash them in. I'll dash this guy in over here too. Dash, 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 dash. And then you can go over here. Dash, 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 dash. Remember, these are particles, so their size doesn't really matter. But like here is the tangential component of this guy, and here's the normal component of this guy. Here's the tangential component of this guy coming this way right here of B, and here's the normal component right here. So we'll label this M B V B1, and we'll label this M A V A 1. Right, so this is the momentum, right? This is a impulse momentum diagram. So there's the momentum, initial momentum. I'm going to label it, but I want to be careful that I don't make it think that it's also there, right? This is the entirety of the momentum, but we could have also broken it down to MB times VB1N, and this could be MB VB1T. tangential. You can see what direction it's going. And maybe I'll do the same thing. MA VA1 normal and MA VA1 tangential. You can either do one or the other. You don't have to label this and label these, but whatever is going to make it easier for you. Now, the big idea, as discussed in class, is that the tangential doesn't change. All right, we could prove that to ourselves by way of this impulse. There's nothing going on in the impulse direction, in the tangential direction. So we could actually just draw each of these pucks individually, and in the tangential direction, the momentum for an individual puck before equals the momentum afterwards. Nothing happens. So we conclude that the velocity after impact in the tangential direction is the same as it was in the initial. All right. Here we're going to have a little bit of a dilemma in terms of our diagram. All right. Because we're not quite sure in the normal direction, which is like just a regular impact in the normal, like just along a line, right? So you could just picture these two things just coming at each other and then bouncing off. Now, sometimes if the large one has a large mass and a large velocity, it will keep going after the impact in the direction it started, right? So it'll just slow down. Sometimes it'll bounce back. So we have sort of a sign convention issue. So the way around that, at least in the diagrams up here, is we're just going to assume the positive normal direction after the fact. And then we're going to assume the positive normal direction after the fact when we do the coefficient of restitution. And then whatever sign that we get for both of these in the final, in the second one, is going to be the direction that they are going, right? Whether it's positive and negative. So assuming positive in both this diagram and in the coefficient restitution, right? So I'm going to assume this guy right here is coming up in that direction right there. So I'm going to put both of them in here. I'll put this in here. So I'm going to say that here is my MA VA2 normal. And this one right here is going to be the same one as the MA VA1 tangential. I should say 2, but it is equal. They are equal to each other. It doesn't change. And for this one, it's going to be a little tight in here, but I'm going to go this direction right in there. All right, and it turns. I guess I'll make this solid line here. So this is going to be my MB VB2 tangential, and then I'll make a leader over here. It's a terrible leader, but B2 normal, right? Now, sometimes I'm going to mess with the angles, but I'm going to go ahead and I don't always do that. I haven't done this in the past, but I'm going to use the coordinate transformation again, right? So let's take these angles that we have right up here. Here's our normal. Here's our tangential. So here's EN, and here's ET. And here is J, and here is I. And the angle that they showed us, well, I got out of those things. The angle they showed us was this angle right there. They said it was 25 degrees. So let's go ahead and keep that. Here's your theta. And if we're going to take a look at this one right here, we can kind of ghost that. And this is theta as well. So the coordinate transformation, if we had ET and EN, and we had like an I and a J, right here we'll draw these in. Okay. For the T, we see that that's going to be the negative cosine theta. Did I do that right? Same one? Yeah, I did that one. Same one. Okay. And then for the J for T, that's going to be positive sine theta. That's kind of a sad looking theta. And for n is going to be positive sine, and then positive cosine. Okay, great. So let's get these original velocities that we have. It can write, maybe just even right up above. We might want to note that VA1 is going to be equal to negative 5 I meters per second, and VB1 is a positive 3 I meters per second, right? So we can convert these into normal and tangential. We could say that VA is going to be, okay, it's just I, so it's going to have that negative 5 times the negative cosine of 25 degrees, right? And that's going to be the entirety of the tangential. And then it's going to be negative 5 times the sine of 25. Oh, almost wrote J. I meant normal, right? So we're just taking an I, and it's just a single column because there's no J as part of the thing. That maybe made it a little easier. By the way, I think this is the more difficult of the three problems, the most difficult of the three problems. Decided that it needed to be in there. It is challenging. Maybe you want to try to do the other ones first. Maybe I should have said that in the beginning, because this one, the other ones do have like a little bit of other challenges in them, but this is probably the most time-consuming and perhaps the one that might frustrate you the most. It's got the most new amount of information in there. We're going to take a negative 5 and trying to figure out where I did with the thing. Okay, there I did. I also made this in Excel, so I'm just checking all of my numbers here. So let's see, in the tangential direction, I think it's going to be 4.532 ET, phone home. And then this is going to be negative. Right, so that was negative, so that canceled out. So this is going to be a negative 2.113. And you should check that yourself. But these are normal tangential, and these are meters per second. I should put some units on there. And then VB, kind of wish I started over to the left a little bit, is 3, right here, right, times the negative cosine of 25 ET. And then 3 times the sine of 25 En. So we get, this should be a negative value, right? It's be, yeah, negative 2.719 ET plus, this, okay, there was negative right here. No, it's not negative. It's going to be positive. It's going to be a positive value. And when we're done with that, we should actually probably check and see that all the signs make sense. All right, so let's see here. We're saying in A, right, that we're going in the positive t direction. This way, right there, right? That sounds right. And then here we're saying we're going in the negative normal direction, right? So we're coming down that way, right? So yes, we're going down. And this one, we're saying we're going the negative t direction. All right, so yes, tangent is that way, and this one's coming this way. Yes, so we got everything right. All right, it's just a good sanity check to make, in case you're insane. Okay, yeah, it's a good sanity check. All right, so I could actually have done this like preliminary, but like maybe I saw that I needed it up here, right? So now I have all these components, and it's really in the normal direction that I'm gonna do my impulse and momentum. So I'm gonna say that the summation of masses times velocity 1 plus the impulse F dt is going to be equal to the summation of the mass and the impulses. The momentums. I said mass times velocities. Okay, momentum plus impulse equals momentum. So we're only going to do this in the n direction. can't spell dir. It's gonna be a long video. So let's take the velocity, and I guess I can write this as symbols. MA times VA1 normal plus MB VB1 normal plus nothing, because they cancel each other out in the normal direction. And now here is where I'm going to keep the signs. Right now, I didn't make the sign convention here. I'm about to in a second. Right, I'm going to take in whatever I had in the normal direction, and that's what's going to be placed into there. All right, for this one when I go to the next step. But I'm just doing symbols right now. We're going to have MA VA2 normal plus MB VB2 normal. All right. And so let's stick some numbers in there. The mass is 2.5 here, and VA in the normal is negative, so minus 2.113, plus my mass is 1.5 for B, so 1.5, and then in the normal direction we have 1.268. Plus 0 equals, and then we can go 2.5 VA2 normal plus 1.5 VB2 normal. And so we do some math here, right? So we put these together, and what we should get is this momentum here is going to be actually negative momentum. Negative 3.381, and it's going to equal 2.5 and VA2 normal plus 1.5 VB2 normal, and this, we'll call that equation 1. We have two unknowns, one equation. So what do? We use the coefficient of restitution, the core, bum, 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 boom. And with the core, we're going to say that VA2, yeah, I guess, nah, let me go for VA1 right now, I think so. VA1 in the normal minus VB1 normal times the coefficient of restitution is going to be VB2 normal minus VA2 normal. Now the big thing is this is the relative velocity initially times this coefficient of restitution. It's going to get reduced after the relative velocity is going to get reduced. It's going to equal, but now this is the negative relative velocity, right? So these have to flip. That A1 minus B1 have to be B2 minus A2, right? So it's A minus B and then B minus A, right? So notice that trend. So these are things that we know, though, right? So we can write this out as a value. And I'm doing it in this order just because it matches kind of what I have up there in that order. I mean, I have a value and then the two things. So A1 is, again, from the sign conventions, 2.113, minus this guy's positive, 1.268. And then the coefficient of restitution is 0.7. And then we're going to equal, and these are the unknowns, VB2n minus VA2n. And we can get a value for right here, and I have a value of negative 2.367 is going to equal this. And that's going to be equation 2. We have two equations and two unknowns. These are the unknowns, and here are the equations, right? So we'll go to another page. V2. So we're going to go combine. Oh, I forgot to write that this is one problem one continued. Keep track of stuff. Dot, dot, dot. And so we're going to combine, geez. Told you, it's going to be a bad day. 1 and 2. All right, so my approach here is just to solve for A. That looks actually pretty good because that'll go over this side, be positive, and this side come over that, be positive, right? So we'll take VA2 in the normal direction, and that's going to be VB2 normal plus 2.367. And then we're going to put that back into here, right there, right? So we'll take negative 3.381. It's going to be equal to 2.5 times VB2 normal plus 2.5 times the 2.367, and then plus 1.5 VB2N. Gotcha. Okay. So now we can solve for VB2. And that's going to be equal to, and I'm pretty sure I got this right, but I don't like how I wrote that down. I do believe it is going to be negative 2.324 meters per second. Let me just double check it. I'll check the numbers. Why not? So I get a 3.381. It's negative, and I have my 2.5 times 2.367 and multiply it, but that's going to be move on to the other side, so we subtract it. So this on this side is a negative 9.298, and then we're going to add 2.5 and 1.5, should be 4, and then we could divide that side out, and sure enough we get a negative 2.324. So, yay! All right, and so now back up from this guy, we can find that VA2N is just going to be negative 2.324 plus 2.367. Wow, it really got small, didn't it? Is that what we decided? Sure enough, yes, it's a very small number. Okay, I need to get, I didn't plan for that, but that's okay. Sorry, I got that thing out of the way. It's 0.04226. I mean, if we had the perfect values, we could actually just, it could make it just stop. That's kind of interesting. That would be interesting. Okay, so that's only part of the solution. What we need to do now is write out the new vectors, right? So here's VA2. In the tangential direction, it never changed, right? So here, right there, this value never changed. So it's still going to be, let's see, I'll write this out here. And it's 4.532 ET. And then plus, now we have this value. And notice it's positive, so it kept on moving, but it almost stopped in the normal direction. And then we'll do the same thing for B. Now, it initially was negative 2.719. It still is. And now its new velocity in the normal direction is negative 2.324 meters. Oh, EN. Meters per second. All right. And it's going to, now we will have to do to be able to get into the velocities, into something maybe more useful, is to do the coordinate transformation again using the coordinate transformation array. Right? So it's a little bit of work, but you shouldn't be afraid of that, right? So we're going to take this ET, we'll see, I'll put it in brackets, and we're going to take 4.532, and that's going to be ET, and we want to get I, so it's going to be a negative cosine of 25. And now we're going to take the EN part of it and multiply it by sine. Okay, so because they're both part of the thing, right? So that's going to be 0.04226, and that's the sine of, I said 25, right? It almost looks like 75. 25, and that's going to be I. Going to do the same thing here. We're going to take our 4.532 and multiply it now by the sine, right? Because there's the tangential component. We want to get the j component. So it's going to be the sine of 25, and then add to it this that component of 0.04226 and times the cosine of 25. We almost made enough room because we still have to say meters per second. Right? And so in the x direction, we're going to get this. It's going to be, I think it's going to end up still being negative, right? So it's still going to be negative. So it's a negative 4.089 I plus, and then in this it's going to be a positive 1.953 J. And I'm sorry for the amount of time this is taking for the video, but you could fast forward it. You could do this all yourself. You don't need me to hold your hand doing it, but I still will hold your hand. But you know, trying to be methodical and thorough. It is okay. So I need this negative 2.324. and multiplied by the sine of 25. Trying to be thorough, diligent. There's a lot of patience that you need to demonstrate when going through a long problem. And do the sine of 25. Sometimes I feel like Bob Ross. If you don't know who that is, well, that's just a shame, but he's a painter that used to do instructional things. And he'd have a nice little calming type of voice. And that's how I'm going to try to do my calming voice, my Bob Ross voice. All right, so there you go. I think I did it right. Oh, sorry, I get that thing right out of the lens. I got to pay attention to that. So much stuff to pay attention to. It's difficult. All right, so you can probably pause it now because you didn't see me write all that stuff down. What a terrible video. I'm so sorry. All right, so we want to write the x and the y for b. Did I do that wrong? Nope. Well, maybe. There you go. Okay. 1.482 I. 1.482 point. Okay. And this should be a negative 3.256 if I did it right. I'm pretty sure I did it right. All right, so now let's figure out what the magnitude is of this square root of 4.089 squared and 1.953 squared. Doing that, you should get a magnitude. Where'd you go, magnitude? Oh, there you are. Of 4.532. That's really what we care about. And we're going to have a theta A of this of inverse tan of rise over run 1.953. 4.08, is that a 9? That's a 9. 9. And what do I get as a theta here? I do believe I should get something like 64.47. Do I do that? 1.953 and 4.089 divided inverse tan. Boom. No. Why? Oh, I see. Okay. That's because, let's see, if I go 90 minus that. Yes, okay. So I should get the 25.53 degrees, right? And that's going to be, notably, this is going to be to the left and down, right? So this is the quadrant that's coming down that way. Okay, going down that way from horizontal. All right, so we're almost there. I know, long video. Long problem. Like I said, this is like the longest problem. A lot of stuff to do. So I'm kind of regretting that I added this one little tag, like part B, onto it, but I think it's insightful. So let's see, this guy is going to be 3.577 meters per second. We'll call it theta B for lack of a better thing. And so 3.256 over 1.482. And not confident with my Excel angles. I'll calculate it by hand here. No, it's not really not by hand, is it? Yeah, now we get the 65.53 degrees. All right, we're almost there. But we also wanted to figure out what the efficiency is. Ooh. What we need to do here is find out what the kinetic energy is, the total kinetic energy before, and then the total kinetic energy afterwards, right? So let's go. KE1 is going to be 1/2 MA VA1 squared plus 1/2 MB VB1 squared. So that's going to be 2.5 times our 5 squared plus 1/2. 3. This one's 3. Is it 3? No, that's 1.5. Yeah, 1.5 and 3. And I end up saying that that's going to be 38.0 Newton meters. And then my KE2, 1/2. I'm writing the thing out. It's going to be thorough. Sorry. My brain wandered. MBVB2 squared. And there's a little bit more work to be done here. 2.5. And here is going to be the 4.532, because it's the total kinetic energy, right? So it's not just the components. You have to use the entire velocity. And here's our 3.577 squared. And I'm saying that becomes 35.27 Newton meters. So one of the things to take away from here is that there's no potential energy. So what happened to this? Well, it just went off into sound and vibration, maybe an itty bitty amount of heat because of the vibration. I don't know. Can't really say, but the efficiency was what you want over what you paid for. And so that ends up coming, what did you want? Well, you wanted kinetic energy afterwards. But what you paid for was all this kinetic energy to start with. And so what you end up with is 92.81%. Right? So, the answers. A is going to be VA is equal to 4.53 meters per second, And as we noted, it's coming to the left and it's going down. And that's going to be at 25.5 degrees. And VB is going to be 3.58 meters per second. And we note that it's going to the right and it's going down. So it's going to come down like this right here. And I'm going to show you a simulation of this here in a second. And then the last one is B, and that's the efficiency is 92.8%. Ta-da. All right, so there's the answers, and I think I got it right. It's a long process. Here is a simulation of this. Okay, so I used Solidworks motion study. I created some parts. These are like little hockey puck things. Let me see how long the video is. Ooh, this is a long one. Okay. Yeah, it's a long assignment. This is the hardest one though. All right. So I got these little hockey pucks, and I made a little sketch right here to try to put them away from each other. And in SolidWorks motion analysis, let me put him over to the side so you don't see him. What I did is, let's see, I'll revert here. I set the thing up with mates to be in the original location, and then I gave them. Oh, by the way, you need to use motion analysis, which is there's animation, basic motion, and motion analysis. So this is actually motion analysis. So this will actually do the kinematics and the kinetics, right? So this is dynamics software. And I gave it, this guy right here establishes the two groups, and I gave it a coefficient of restitution of 0.7, just like the problem, right? And then I also gave each of these parts, you can click on there and you can see initial velocity. And so I did that initial velocity for each of the parts, edit. So you can see here's that part of 3 meters per second, and here's the direction. And I use that sketch to give it that line. And the same thing true for this one right here, right? So that's the way I set it up, 5 meters per second, go to the thing. And then I arranged these things with to get them in the correct place. So I got them, I picked a distance like that would be, I think about 1 second. So I was trying to get the collision to happen 1 second later. So I worked backwards. But then like you could see, here's the concentric thing. You suppress this, right? So that it's unsuppressed right now. I'm going to suppress it. And let's see, I think that's about it. All right, so I made the other mates are that it's constrained to be on this table. And then I set, here's other things in case you wanted to try it yourself. I get 500 frames per second. I decided to pick it on after I messed around with it. And I also picked a precise contact. All right, so let me see, and we can see, boom, right? So there you go, like you can see it again. Boom, and I even, on the sketch, this sketch right here, I went ahead and picked what my answers were. So you can see it's it's supposed to be on that line right there. That's what I said my angles were. So that's my solution look like this. So let's see this thing again. It won't let me go any more slow motion than 0.1 onto the thing in terms of it. So it is happening very quickly. But you could see that we have the same results. Now one thing I can do as part of this is I could go, you gotta be careful that you don't change stuff in the middle. You want to change stuff at the beginning of the thing. But let's see what happens if I change the coefficient of restitution to, let's say change it to 1. Let's see what happens. The coefficient of restitution of 1. Well, I'll solve it. Boom. So, oh, that's interesting. Okay, I also have it made so that you could see the vectors on there. I need to go back. Let me. I'll change this back to that same coefficient of restitution. But so we can go 0.7 again, and solve. Boom. Now it's back online. You can also see if you could make the graph big enough. We can export this information to Excel, but it's kind of like, I've never been able to figure out how to like get the information. But see right there, here is the initial velocity 5, and it drops down to where it looks like right now 4 point, it's less than 4.6, well 4.5 something. And isn't that what we got? Isn't that what we said it was going to be? 4.5 something. Sure. All right. So we're confirming our work. And then here in the red one, it starts out at 3, and after it's somewhere a little bit more than 3.6, right? So, or 3.58. There you go. It's pretty darn close. This is, and one of the, this is just confirmation that this is working correctly, but I had to monkey around with it a bunch, right? If I hadn't known what the numeric answer was, I might have made mistakes in the way that I set up my boundary conditions and stuff. So the computer is not a substitute for trying to, knowing how to do it by hand, but it sure does give you a little bit more confidence in your solution. And my doing it by hand gives me confidence in the numerical solution as well. But I needed to know how many like frames per second that I needed to go onto the thing to be able to get a good result. But we can monkey around with it, right? So we could say, what would this look like if this was a 0, right? Let's see, they're going to stick to each other now. Let's see if it'll actually do it. Nope, they didn't. See, it didn't work. That's sad. That makes me sad. Why? Well, so with a 0, they were supposed to stick with each other, but I guess they just that's not in their command line right there. But this is a lot of fun to do stuff like that. But to be able to have the fun stuff of doing the computer simulation stuff, which I've always enjoyed, you have to also eat your broccoli. You can't just have your dessert. You have to eat your broccoli, which is the hard work of doing stuff by hand and that kind of thing. So that's what I have for today's video, and it's 42 minutes long.